Hello. In this video, we'll talk about Ampere's law. Ampere's law is a convenient tool in order to find magnetic fields from various current distributions. What Ampere's law states is that if we have a wire that carries electricity, then we know that this current generates a magnetic field around the wire. So we consider that there is a closed line, a closed Amperian surface, Amperian loop around the wire that contains this current inside it, the current enclosed. This current multiplied by the constant of magnetic permeability in vacuum is equal to the line integration of the magnetic field with respect to the length of this line. Now, this law helps us find magnetic fields in slightly challenging charge electric current distributions. Now, in this example, we'll try to apply Ampere's law and sketch the results of Ampere's law. Now, on the first part, the question states that we need to determine a magnetic field at a distance r away from a wire. So we are on the example that we're just mentioning here. However, this wire is not a long, thin wire. It is a wire that has a radius r. So we need to find the magnetic field at a distance r away from the center. This r away from the center is a variable, so we call it with a small r, in order to differentiate it from the radius of the wire, that it is a capital R. Now, according to Ampere's law, the integration of magnetic field with respect to the length of the Amperian loop of radius small r is equal to the current enclosed multiplied by the magnetic permeability. The magnetic field multiplied by the result of the integral of the dl is the whole length of the circle. So it is 2 pi r is equal to mu multiplied by current enclosed. And from this we bring that the magnetic field at a distance r away from the center of the wire is mu multiplied by current enclosed divided by 2 pi r, which is very, very similar to the magnetic field of a long straight wire, around a long straight wire, the law that we already know. Now, the slightly challenging part comes to what happens if we need to find the magnetic field inside the conductor, inside the wire. So, if we select a distance small r away from the center of the wire, then the current that flows there is not exactly the same like the current of the whole wire. For example, if the total current in the wire is 10 amperes, then the wire that flows inside this cross-section is for sure less than 10 amperes. It's going to be a fraction of this 10 amperes. So we need a tool in order to calculate what will be the value of this current with respect to the total current. For this, we're using the concept of current density, where we remember that the current density, J, is equal to the current divided by the area. Now, if we select the whole cross-section of the wire, the area of the whole cross-section of the wire is pi capital R squared. And the current that flows in this area is the total current I. However, the current density is also equal to the enclosed current inside this Amperian loop. So we call this I enclosed, divided by the area of this small circle, which is pi times small r to the power of 2. Now, these two factors will be equal because the current density is the same no matter where exactly on the wire we are. So we have that I divided by pi r squared is equal to the small enclosed current divided by pi small r to the power of 2. Pi and pi becomes cancelled, so the current enclosed is equal I multiplied by small r squared divided by capital R squared. Now that we have an expression for the enclosed current, it's quite easy to go to apply Ampere's law, so magnetic field multiplied by the length of the loop is equal mu0 multiplied by current enclosed. So magnetic field multiplied by the length of the small loop is 2 pi r is equal to magnetic field multiplied by I times r squared divided by capital R squared. 1r with 1r is cancelled, and we get that magnetic field is mu O times current times R divided by 2 pi r squared. And what this means is that outside the wire, that inside the wire, the magnetic field is directly proportional to the distance away from the center. So as the distance away from the center increases, there is stronger magnetic field. And linearly proportional, this means that the magnetic field will be increasing as a straight line. However, when we reach the surface of the wire, and after that, so outside the wire, the magnetic field is inversely proportional to the distance. So as we go away, the magnetic field decreases. So inversely proportional magnetic field means that the magnetic field will be decreasing as a hyperbola as we are moving away from the wire. As a result, have in mind that applying Ampere's law is not a difficult thing, it's not something difficult. However, it can be quite challenging in cases that we don't know the current inside a certain surface, that we might need to use the current density in order to find the enclosed current inside the Amperian loop. Thank you.